Okay, so if potential energy is equal to the magnitude of the test charge times the potential from all the sources, whatever the sources are. Okay, well, what is the potential of a capacitor? Well, we found for a capacitor, okay, it is equal to test charge times the electric field of the capacitor times S being the distance from the negative plate. So here's the negative, here's the positive. So if I have a charged particle, some Q test, we'll just say it's positive just to make it look like a charge. This is my 0, and here's my S, and we'll call that D. So at this point, this is some S initial, wherever it's at, and that's what the S is. So S is a measure of the position of the particle from the negative plate. So if the particle's all the way over at the positive plate, then it's at D. Okay, so that's what S means. It's really important to keep that straight. Well, if we compare these two equations here, then we see that for a capacitor, okay, the potential across the capacitor is equal to ED. Okay, it's the potential across the whole thing. And I'm going to be a little more careful now that I've introduced this. We need to properly reference the difference instead of just a value. We could somehow establish this as being a 0 potential, but we actually would have to control that by some global reference point. We'll see that later. Like with potential energy, we assumed that this is at some U naught, or we chose it just to be 0. And we can choose that all we want. Okay, but potential, we need to be careful, especially as we get into circuits, that the potential is somewhere globally referenced as 0 and everything's measured from there. So to not have to worry about that, we can just talk about potential differences. So whatever the potential is here, we can call that V at 0 and V at D. Okay, whatever it is there, we do know delta V is equal to ED. Okay. And we could have said, well, what's the potential here? Well, we could say that the potential here is V0 plus the E times SI. Okay, so the potential right there would be V0 plus ESI. Okay. It's whatever you started with, and we moved in the positive direction of S, so we gained that much more potential. Okay. But again, what really matters is a potential difference across that between here and here, because that will affect a potential energy difference from which we can determine a work done or a speed or kinetic energy. Okay, so potential difference is what's important. And we can see that for a capacitor, when you go all the way across the capacitor, the potential difference across the capacitor is the electric field inside the capacitor times the gap. Okay. Now let's go ahead and take this a little further, because we know that Q over A over epsilon 0 is the electric field of a capacitor. And so now we have the potential across the capacitor. We can simplify this QD over epsilon naught A. And so the potential depends on the size of the charge in the capacitor, the area of the capacitor plates, and the gap between them. So potential changes based on the gap, which we saw and emphasized before. The electric field doesn't. The electric field is constant everywhere. It doesn't matter how big the gap is. Okay, but now the potential grows across the gap. So one way of looking at that is if I redraw these capacitor plates, can I imagine graphing? Okay, up this axis is my potential, and across this axis is S. And this is actually my negative plate and my positive plate. Then I could choose this to be 0, for example, for this case. And I could say, okay, it starts here, and it'll grow linearly across. Now, this is a little foggy, and so I'm going to try and draw it one more time. I'm going to actually have a separate graph of S and V. And then I'm going to just say, okay, I'm starting right here. What am I at? Okay, I'm going to be more general now and say, oh, I'm at some V0, whatever that is. Could be positive, could be negative. I'll just go ahead and choose it to be a positive value right there. That's what I'm at when I'm at S equals 0. Well, what if I go a little bit further across? All right, well, it is now grown some amount of E times that little bit of S. What if I take another step? All right, well, that's going to grow the same amount because it's a constant growth, and so on and so forth. As I step across here, it's going to just grow linearly until I reach a point of, at this point here, if I get to D, which I didn't get my axis long enough, the value here would be V0 plus ED, or V0 plus delta V capacitor. Okay, and so that's what's going on here. And it has the same idea as going from here to here, and then to here, and then to here, and then to here. Well, it only depends on distance from the negative plate. So if I go along or parallel to the plate, the potential doesn't change. So this is all at the same potential. These would all be at the same potential. And because of the way that the electric field's pointing, well, the electric field is pointing from positive to negative, and so my potentials are growing in that direction. Okay.